Right, welcome back. This is the third question in the June 2010 AQA AS Physics Unit 2 course. So this question says, 3A, it says, define the amplitude of a wave. Now, I'll just draw a wave out so I can, when I'm explaining it, it might be a bit easier. So this is a standard wave. I'm not really bothered about what type of motion it is. Third harmonic, I think it is, or second or first, I don't know. That's not important. Well, I do know, but it's not important for this question. It said to find the amplitude. Now we know the amplitude is this, the maximum height, if you like. You can also draw the wave as this, because light behaves as particles, a wave behaves as particles, etc. Use the de Broglie wavelength, which we cover in Unit 1. To explain this. Now these are all vibrating particles. Now they are a distance away from the horizontal, the equilibrium position. I just put E. Now, if it was a distance, if it was distance, it'd carry on increasing away. But there are nodes or intersects and antinodes, which we're going to if you look at the waves video of the course. So we can say it's the displacement. We know it's got to, the definition's got to include displacement. It's got to include something about the vibrating particle and the equilibrium position. So this is a key definition. I'm going to write it down because I've just tried to show you. The maximum displacement of a vibrating particle relative to its equilibrium position is the definition of the amplitude of a wave. Hopefully you can understand that. And I've tried to explain it, and you've not just drawn this line and said that's the answer. Otherwise you could just look at the mark scheme. Now the next question, 3B, it says other than electromagnetic radiation, give an example of a wave that is transverse. Now transverse waves oscillate right angles to the direction of motion, so another one than transverse. Other electromagnetic even. So see what they've put here. You could have, you could have the wave on a rope, so you're swinging it left and right. The wave's going transverse, right angles to where it's actually heading. So you could have a rope. I'm only going to put one down because it's only asking for one. So you could have a rope. Now if you want to look at any more, as I said, you can just look on the AQA website for them. It says, we've sort of said this, but for 3C it says state one difference between a transverse wave and a longitudinal wave. And so a longitudinal oscillates parallel. I'm just going to put this in note form. Parallel. You need to put oscillates parallel to the direction of motion, to the direction of travel. Transverse, we've sort of said it before. Parallel. Perpendicular. You just replace parallel with perpendicular and point writing the whole thing out again. So they're the two things you need to put down for the 1 mark. Or you could just simply say the different ways they oscillate, but you make sure if you're in that exam you want to cover all bases, so make sure you put the way they oscillate and establish to the marker and the examiner, it might be me, you know what you're talking about. So next question, 3D, says, what? Oh, 3, what? Sorry, that was 3B part 2. I'm just skipping ahead. 3C part 1, sorry. confused with numbers. So just the questions are in order. Right. So it says, the figure 3 shows two identical polarizing filters. So I'll just draw the diagram if you've not got it up. Two polarizing filters. Oh dear. Never mind. For those of you who don't know, a polarised wave is ones that oscillate on a vertical and horizontal plane, so they are not plane polarised waves. So it goes through this one, it polarises again, polarises, so that means it only oscillates horizontally, and it does exactly the same when it goes through this. Now what does the question say? Well, it's got a little eye here. I'll draw that for you. So it's great seeing the scientific eyes. That's your observer there. Give him a few eyelashes, why not? There's a fancy guy. Oh, sorry. Polarised light is reaching the observer. Draw the direction of the transmission axis on the filter B. So the transmission axis is the way the molecules are aligned. Now, if you've got a wave that oscillates on a horizontal plane, if you've got the molecules that are aligned vertically, they're not going to be able to get through, as the wave will be too wide. If you've got a wave that's got a slit like that, if you can imagine, so the waves can get through for vertical, but if they're horizontal like this, all oscillating horizontally, and you've got a wave, you've got a oh god, that looked really weird, but never mind. You've got a transmission axis that is vertical. If you've got a horizontal wave, it's going to get through. If they're both vertical, then it'll get through. But if it's horizontal and vertical, only the vertical will get through if the molecules are aligned vertically. So basically, it's going into the first one as a unpolarised wave, coming out as a plane polarised, so it's vertical, and then it's doing the same. So we can say the transmission axis for the second one is exactly the same. So that's your 3C part 2. All you need to do is that dotted line vertically. 3C part 2. What does it ask us? It says the polarising filter B, which is this one, is rotated clockwise for 360 degrees about line XY. And if you don't know what XY is, neither do I. From the positions shown in figure 3. On the axis below, sketch how light intensity reaching the observer varies as this is done. Okay. Right. So, what it's got here, is a table. It's got 90 degrees, 180, keeps adding 90 each time, 270, 360. Now if it's oscillated that way, it's turned 90 degrees, so that way it's horizontal, molecules are aligned, so if it's coming in vertical, which it always is, as it's going through A first, so there is no light intensity, so we could say it's on the bottom, so we just draw an X, put it on the bottom. And for 180, if we oscillate it that way, it's basically upside down, but the molecules are exactly the same, so maximum intensity. For 270, we rotate it again, so it becomes horizontal, so as a wave oscillates vertically, can't get through, so light intensity is 0. 360, back vertical, so back where it was, so the light intensity is 100. So if we join them up, it should look something like this. Obviously with only a few getting through, that's why there's a little bit getting through, but majority of them won't. Just making sure that's the right way. So that's your diagram. Right. So for 3D, finally on 3D now, it says, state one application other than of education, a polarising filter is used, and give a reason for its use. Now the main one the examiners like to hear about is polarised sunglasses. and that's just to protect your eyes from the powerful rays of the sun. So just polarized sunglasses or sunglasses. I'm just going to polarized sunglasses. These are the expensive ones. It's just like charging $1 billion for them. Obviously I have them in GTA, but we're not playing GTA, we're playing physics. And the game of physics is very tough, just like the game of life, but the game of life can crush you in an instant, whereas physics crushes you slowly, but force is spread out, so you feel less force. Bam! So, other than education, so polarised sunglasses and then to protect your eyes. Quite simple really, that. The rays are very concentrated from the sun, this sort of takes some of the energy away from them. That's question 3 done. We'll see you in the next question for AQA AS Physics.